Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on impulse and momentum, and it's section 2, and it's the second in the series, and it's about loss of energy due to impact. So look at the story so far, and that is, in a collision between two objects, we discount external forces acting, we suppose that the collision takes place instantaneously, and we take it that momentum is conserved. Now, momentum may be conserved, but there's likely to be a loss of energy. Indeed, the energy is pretty certain to change. So it's a good question to ask, what kind of energy loss are we going to expect? So the change in energy is always the final energy minus the initial energy. That's the best way to look at it, and so you'd expect to find that that's negative because some energy will be lost and transformed into other forms such as heat and sound, or maybe even light as well. So looking at the restitution law, we remind ourselves that the coefficient of restitution is the ratio of the separation speed to the approach speed, and there are the two special cases of perfect elasticity and perfect inelasticity. We're looking in this case at the change in kinetic energy, which is the final minus the initial, and we expect often in collisions to find that there is indeed a loss, so we expect a negative answer. There's our first case. Well, it's simply a matter of remembering that the formula for kinetic energy in general for a body is or particle is half mv squared. So if we take that, then the change in energy, is going to be just a matter of applying that formula systematically. So the final energy is going to be a half times 6 times 3 squared. That's the kinetic energy of the first body, and then add to that the kinetic energy of the second one, a half times 1 times 6 squared, and from that we need to subtract the initial kinetic energy, which is a half times 6 times 4 squared, and it's going to be added to that nothing, because the right hand particle or body is 0 velocity. So those are the calculations we're going to have to do. So doing those quickly, we're going to have 3 for the half times 6 times 9, that's 27, and then we're going to have a half of 36, which is 18, and from that we're going to have to subtract 3/16 are 48. So we do that calculation, and that will give us the answer. So there we are, that repeats my figures, and we end up with the final answer, minus 3, which is interpreted as saying that 3 joules of energy are lost. Now let's look at another case. In this case we've got a slightly more complicated diagrammatic setup, because we obviously got the sense of direction wrong when we did the calculations here, and ended up having to say that that arrow has a minus 2 on it. In other words, the particle or body is moving to the left at 2 meters per second. So again, our change in kinetic energy is worked out by the usual formula. So the change in KE is simply half times 3 times, and we can ignore that sign because we're squaring the minus 2, so it's a half times 3 times 4 plus a half times 4 times 16 for the 4 squared, and from that we subtract a half times 3 times 6 squared, that's for the left hand particle, and added to that within the brackets is a half times 4 times 2 squared. Bit of a squeeze there. So we need to work out all those figures. So this first one is going to be 2 3s are 6, the second one is going to be 2 16s are 32, and then minus it's going to be 6 6s are 36, divided by 2 is 18, and then times 3 gives 54, and we'll have 8 for the other contribution, so that's 38 minus 62. So that should give us an answer, and it's minus 24. So there's the figures, there's the answer, and we interpret it in context. As a result of the collision, 24 joules of energy are lost. Now a final example, and this time we have a case of coalescence. So once more, the change in kinetic energy will be the final kinetic energy, half times 3 times 4 times 0.8 squared, and it will have also a half times 2 times 0.8 squared. You could, I suppose, say that if they've coalesced, that's a single particle of mass 5. It would give you the same answer, half times 5 times 0.8 squared, and from that we subtract half times 3 times 4 squared added to a half times 2 times 4 squared. Notice that when dealing with energy, signs for velocity don't matter because you're squaring and everything will turn out to be positive. So that's our calculation which has to be completed. There's the summary of the same figures, and the answer turns out to be minus 38.4. So the conclusion in context with the units is that 38.4 joules of energy are lost. Well, that brings us to the end of the video on the loss of energy due to impact. The next one is looking at more elaborate collisions involving more than two particles. I hope to be with you later to explore that.